Hello everyone, how's it going? My name is Dan the Tutor. Today we're going to be talking about thin film interference, and these are examples like this. So let's say I've got two surfaces here, pretend those lines are straight, and on one side I have air, in the middle I have some film, and on the other side I have another layer of air. Now this film is going to have some thickness T, and basically light is going to be entering the air. And you probably remember from Snell's law that some of the light is going to refract, which just means bend and go through it, and other light is going to reflect and bounce off like that. And then once we go from the film back to the air, again, some of the light will refract and more of the light will reflect, and then it refracts again. And this is the picture of what's going on here. Now what's important here is these two rays, because it's possible that they can either add constructively or they can add destructively. And when they're added constructively, those two arrows, I'll tell you that the light is going to be amplified, like it's twice as strong as before. And if they add up destructively, well then that's when the light is going to be blocked out. In other words, you don't see the light anymore. And here's the equation we're going to use to determine if the light was constructively added together or destructively added together. The equation is 2 times T, where remember T is the thickness, and then times N, where that is N for the film specifically, not air on the other sides. And that is equal to M times the wavelength of the light. Now M is the cool part because M, depending on if you have constructive or destructive, if you have constructive interference, well then that means M is going to be 0, 1, 2, 3, ... It's just an integer. And if you have destructive interference, well then that means M is going to be all of the 1/2 values like 0.5, 1.5, 2.5, etc. The list goes on. Now typically, we always want to use the smallest value possible for constructive and destructive when solving these equations. So for instance, for destructive, you would always use m equals 0.5, and for constructive, don't use 0 because that's like a weird case. Just use 1, like ignore the 0. And these are the values we use when plugging into this formula. Now this is basically everything you need to know except for the most important part, which is it depends on if there is a phase shift or not, which also depends on the index of refraction, which is what n is. So for air, let's say n equals 1. For the film, we'll just make up a number, n equals 2. And for air again, n is 1. Here's what you need to know. When you go from a low to a high index of refraction n, like from air to the film, for instance, then you are going to have a phase shift. And then we compare that to when you go from high to low, there is going to be no phase shift. And you really only want to look in the forward direction. You don't want to look at the reflections. So what do I mean by that? If we go back to our picture, what I'm saying is you're only looking here for the phase shift and here for the phase shift. You're not looking at the reflections. So basically what we would say here, when you go from n equals 1 to n equals 2, there is going to be a phase shift right there. And when you go from n equals 2 to n equals 1, that's lower, so no phase shift there. Now let me explain what the phase shift means. It's not that hard. But basically when I say phase shift, I'm specifically talking about a 180 degree phase shift. And whenever you have a phase shift, you need to switch constructive and destructive interference. That's the easiest way to put it. What used to be the values for constructive interference are now destructive. And by the way, a lot of people say destructive is m plus 1/2 times lambda. A lot of people use this for destructive interference. But I like my way better, where I just say m is the half values, because I think it's more straightforward. There's less thinking on your end, so I like using the half values instead. But as you can see in this picture, there was one phase shift. Agreed? Phase shift here, no phase shift there. So if you have one phase shift, like in this example, then you are going to switch constructive and destructive interference. And then if you have two phase shifts, in other words, you're going higher twice, or if you have no phase shifts, because this will also be the same thing, then you don't switch the equations for constructive and destructive interference. You don't switch them. So let's look at a couple examples. Let's say here we have a pocket of air where again n is 1. Then you have your film in the middle where let's say n equals 1.4. And then on the other side you have air again, which is n is 1. I'll tell you the thickness is what you're going to be solving for. And my question is, what is the thickness to block out light with a frequency of 4.29 times 10 to the 14th hertz? Okay, so I don't even need to draw my picture of the rays, but if I wanted to, a ray's going in, it's going through, it comes out the other end, some of it bounces back, and then some of the light reflects. So that's the picture, but I don't really care about the picture. What I care about is two things. Number one, the equation, which is 2Tn equals m lambda. And second, do I have one phase shift, two phase shifts, or zero phase shifts? Well, if you look at this point right here, when we go from air to the film, that is going to be a phase shift right there. And then when we go from the film to air, again, there's no phase shift. So that means we've got one phase shift total. It means I am going to switch. So now if I want constructive, it's the 0.5 values. If I want destructive, it's the whole numbers. And do I want constructive or destructive interference? Well, 99% of the time, we want to block out light, or the question asks about blocking out light, which means usually we're talking about destructive interference. So since I want destructive interference and it was switched, that means m is going to be 1. Because normally m equals 0.5 for destructive, but since we had the switch, destructive is now all the whole numbers. And remember, we always want the smallest value for m, so then we're going to use m equals 1. Now basically we have everything we need. 2 times t, n is 1.4, so I'll plug that in, equals m, which is 1, and then lambda, the wavelength, is the only thing I don't know. Now I did give us a frequency, which means I can use that to find the wavelength, because we are talking about light, which means I can use the equation c equals lambda times f, where c is the speed of light, 3 times 10 to the 8th, and lambda is what I'm solving for. F is 4.29 times 10 to the 14th hertz. So I just divide both sides by 4.29 times 10 to the 14th. And if you do that correctly, you'll get 7.00 times 10 to the minus 7th. And the units for that are meters, not that I really care right now. But that's what I'm going to be plugging in for lambda. 7.00 times 10 to the minus 7. And then if I want to solve for thickness, I just divide by 2, and I divide by 1.4, and I will get a thickness of 2.50 times 10 to the minus 7th. And again, that is meters. Which, in case you're curious, that would be 250 nanometers if you wanted to convert to nanometers, because it's 10 to the 9th power for nanometers. And so that's this first one. Not too bad. Now let's just look at one more. Let's say you want to design a space helmet to block out light from the sun. You put a thin film coating on the glass of the helmet. The helmet is made of glass with an index of refraction of 1.5. If the film has an index of refraction of 1.2, what thickness do I need to block out light from the sun? Let's say that's a wavelength of 500 nanometers. Okay, so here's my problem. Now let's start out by drawing a picture of this. Let's say the three regions are air, which is n equals 1, the film that you're putting on top of the helmet, which is n equals 1.2, and then you have the actual glass from the helmet, which is n equals 1.5. And if you didn't know how to figure this out, basically if you imagine this helmet in real life on this astronaut, and I'll draw the film coating in red because that's basically what it is. It's a very thin film coating on the outside. You've got air, you've got glass on the helmet, and then the red is my thin film. And if I zoom in there super close, this is what I'm looking at right here. I'm not even going to bother drawing the arrows this time because I don't care. But one thing I will say is that I'm going to have a phase shift here because I'm going to a higher index of refraction, 1 to 1.2, that is higher. And then I get higher again when I go from the film to the glass. So there are 2 phase shifts this time, which means no switch. I'm going to keep constructive and destructive the same as they normally are. And since I want to block out light from the sun, that means that I want destructive interference again. And since there was no switch, m is just going to be 0.5. So now, again, when I plug in my equation, 2Tn equals m times lambda, I'm solving for thickness, which we normally do. N is the index of refraction of the film, which is 1.2, equals m, which is 0.5, and then this time I give us lambda, it's 500 nanometers, but I do have to convert nanometers to meters. That's very important. So let's think about that real quick. 500 nanometers, I do some dimensional analysis. There are 1 times 10 to the 9th nanometers in 1 meter, so I'm dividing by 10 to the 9th, and that will give me 5 times 10 to the minus 7th meters. So that's what I'm going to multiply by right there. And then again, to solve for t, I am just dividing by 1.2 and dividing by 2. And let's plug this in our calculator and see what we get. 1.04 times 10 to the minus 7th meters. Or again, if you want your answer in nanometers, because sometimes they ask for that, this would be 104 nanometers, because you'd multiply it by 10 to the 9th. And that's going to do it for thin film interference. There's, I suppose, more types of questions than the ones we just looked at today, but this is going to cover most cases for thin film interference. Again, the most important part is remembering how many phase shifts you have, and that depends on how many times you're going up or down. Oh, and by the way, for this last one, let's say you wanted to go for light going from the other way. Let's say you didn't know which way light went. You wanted to go this way instead. That's fine, because since you're going lower both times, that means there's no phase shifts and there's no switch again, because there's no phase shifts when you go from a higher to a lower. So regardless of which direction I'm going and I'm looking at this light, you'll get the same answer anyway. It's either 2 phase shifts, which means no shift, or it's no phase shifts, which is still no switch. And the same is true if there was 1 phase shift. It doesn't matter which way you go, so you can mess up that and still get the right answer. But you need to remember 1 phase shift is a switch. No phase shift or 2 phase shifts is no switch on the constructive and destructive interference. So if you have any questions, please post them in the comments below. Thank you all for watching, and I'll see you in the next video. Take care, and bye-bye.